Yeah, I pressed that plus button yesterday. I started using a Fargo, right? Yeah.
Hello, everyone. Whoa, okay. Hello, everyone. Hey, please. Come through the. Good jank. Yeah, we'll be talking through the problems.
Oh, wait.
Yeah, the mic is like. Can we like make more? Make it a little bit.
Oh, yeah. Yeah, because I thought like. You can get his mileage, bro. I like cut it off. Around like 4 miles. Like the issue I have with it is like, it's like the Python thing, right? Where I have to scan it in as like a string and then split it. So like they're like they're sort of like it's so hard to do error checking. There are a variety of methods. It also has the asset string string things. Which again annoying. You can always just cast them to there are a few annoyances compared to C++, but mostly they're things that are actually a really bad idea. I just like it C++. It's not Rust, C++. Yeah. I looked at some values. There's like some like optional stuff. I don't know. I think Rust. I don't think I've seen it. Have you? Right. Rust. I didn't get the Rust. It's in the Rust. It's like something that don't like and a result is something that I just petty. So sure, it's wrong. You know, like the macros. It's just like not macros. That's what it is. It's not really why do you love math? Wait, how does moving work? Like, I'm like at the top when I'm like including stuff, right? Like why do I have to include this stuff? Like the dots here. Like, it's okay to like run a command. When it's in the file, you can do it. I know abstract. I did some learning questions in the program.
All right, 3 solves. Like kind of got like knowledge checked by D, I think.
Okay.
The deck.
It's just so tragic. It's like sort of like it's like I put it in the top one.
All right, everyone, come down to the front and let's talk through the problems. So today's contest has 7 problems. The problems were courtesy of the Nordic Collegiate Programming Contest of last year. So thanks to the jury from NCPC for writing these problems. As usual, we took the 7 easiest problems. There are 4 other problems, and I will put up a practice set containing all 11 problems in the coming days. So yeah, you can expect that to go up very soon. Yeah, so there were 7 problems, and the easiest problem was problem C. Yeah, given a number, write it as 2s and 3s added together. I hope I don't have to talk about this one too much. Yeah, like just about anything works. Yeah, you can do anything. Just about everyone solved this. I think there's nothing to talk about. All right, problem K, we want originally called K, but in our contest it was called E, empty space. We wanted to center the pattern. So given the width of the pattern, we'd stick it in the middle and then tile left and right until we had some overflow space at the leftmost and rightmost edges. That was.
Hi, boss.
Do a bit of just how many of those tiles you can place each side. You have an n of n minus p all divided by 2 space left on each side after placing the centermost tile. And you fill this with as many p's as you can, like with p blocks, and work out how much is left over at the end using the modulo operator, and then double that because you can have the same space on the left and yeah, the complication is that it might be possible to fit one more pattern exactly around the back, so make sure that you adjust for that. All right. happily, this is one of the sample cases. So hopefully you were able to detect this error even if you had that bug. Right, those are the two most trivial problems. And then from there, I think things get a bit more interesting. So I will hand over to students to take you through the rest of the 5 problems. Who wants to talk about A? Frank?
Yeah. So the thing with
It's just
is it,
I hate this.
is it easier? Don't use a mic. Can everyone hear me?
The recording might be.
Oh, okay. I will use the mic then. With problem A, there's actually quite a lot of things we don't know. So all we're given are the starting and end points, which don't have a pool, and we're given one point that is within a rectangular pool. But there's actually a ton of information we don't know.
I can actually just illuminate a bit about this. Basically, the way the judging worked in this problem was in every test case, other than the samples, it was like the coordinates of the pool were in the test file, like in the input file. So so yeah, the actual format of the input files other than the samples was like start point, end point, given point, left, like low left and high right corners. So there were 5 lines. And then for the samples, the validator had something hard coded for what the pool was. Yeah, so there is like a fixed position of the pool. You just need to solve for that fixed position, but you don't know what it is. Yeah, if you hacked that, props, I guess.
Yeah. So the key thing to note is that I don't actually think there's a consistent strategy that stays within a reasonable bound. There can like often be some kind of breaking case of like maybe the pool goes in towards that direction or extends further towards that direction. The key thing to notice is that there are constraints. Mind if I show it? Yeah, so the pool is constrained by those values, so between negative 1,000 to positive 1,000 along both axes. However, the points you're allowed to travel along greater amount. Oh, sorry, I know my zero is 10,000. Thank you in all directions. But the points you're allowed to travel towards, I believe, are 10 to the 9 in all directions, which means that you can go quite easily outside a range, which definitely will never have the pool. And yeah, so the observation is that you can't intersect the pool up from the pool point, because that would imply, like if you did, that would imply that one of the points are already inside the pool, which you're given is never the case. So you can always move outside of that, travel in the range that is safe from the pool, kind of wrap around, and then go back to the end point you're trying to get to. Is that the only page? Oh, okay, easy. So you're given X, you kind of just move in a immediate line away from it. You also do this in like horizontal or vertical ways if you don't want to do a diagonal way. But the idea is you just move outside to a definitely different, kind of wrap around because it's definitely safe to do so, and you just kind of cut straight in. Yeah. Hopefully makes sense to people. I think that's it. Yeah. Anyone solved I? This was B.
Yeah.
Okay, so the problem statement was you are given some amount of money that this person starts with and some interval upon which they are given some new amount of money. So I think the initial amount of money was M, and every D days they are given an extra S money. And at the start of every day, they spend half of their money rounded up to the nearest integer. The hardest part of this problem was reading the statement and figuring out whether it was 0 or 1 indexed. So instead of the numbers being given, the numbers are extremely large and they are given as binary strings. So you can't store them in a single integer. You just have to store them as like a Boolean of vectors or something. However, this actually makes it quite easy to do most arithmetic. So dividing by 2 is just popping off the last thing, and addition, you just implement a bitwise adder. So there are 3 different cases. The first case is that the length of the initial money you're given is less than the number of days before you're given a paycheck, in which case you run out of money before you get any money. And so your answer is just the length of the initial money you're given. Otherwise, it's the case that the amount of money in the length of the size of your paycheck is larger than the number of days, in which case you will end up with infinite money. And then the final case, you'll end up with finite money, but you will get some number of paychecks. In this case, you can just simulate it, and because the size of your money is at most 1,000 and the length of your money will be decreasing by 1 each iteration, it's going to be at most order n squared or something. And yeah. So yes, in this case, they've just shown an upper bound on the number of days overall and simulating just if you don't go broke by that point, you have infinite money. And then that is the special casing for if you know that you will go broke quickly or have infinite money.
You can just like, if you get
So that that's just the implementation part.
By the way, at any point, if you have a question about, why you approach it work or some observation that you didn't quite follow, please feel free to jump in and ask. But yes, the next program will be the.
So like kind of like this, because like the worst case.
So longest common subsequence problem for each value occurs almost 15 times. So if you did the naive, like longest common subsequence problem, it's O of n squared. But if you sort of look at like what's happening in like the DP, you have a, should I draw it? Actually, it's fine. You have a grid.
Yeah, but you can like.
Is there a marker? I have a marker. Oh, it's fine. I'll just talk about it. So the DP works that. Oh, sure.
You did the DP?
Yeah. Like it's like a DP, but like you like speed it up with the secretary.
Only by symmetries.
Yeah, you solve it. You like speed it up with the secretary. But like your DP works. I'll just use this one. It's fine. Like your DP works where, like let's say that's your table, and then this is like the index of the first array, and this is like the index of the second array. And if I had like values lined up, whenever like the value is the same, then like you take this value, like you can either take this value or you don't. So if you take the value, then you increase the iterator like both. Otherwise, you just take that one or that one, right? This is a very bad explanation, but like it works. And yeah.
Like n is 10,000, right?
Yeah.
So size of the DP is like 10 to the power of 8.
Yeah. So this is why you speed it up. So the way you speed it up is you can think about each of these points where it's the same value as like a coin, right? So then you change the DP problem to like a path problem where you start from like the top left corner to the bottom right corner, and you want to pick up as many coins as you can. And each time you pick up a coin, you move diagonally. Otherwise, you can move right or down, right? And then this is a pretty standard problem you can do with a secretary. So you have a secretary lengthwise that stores max and like that supports like max query and like point set. And then you have the secretary like lengthwise, and then you get to a coin, and then, or like for each position, you just query the max beforehand in the row above. And then after you process the row, you just update everything in the secretary, and you go down and you take the max in the secretary. Does that like make sense? I hope so. Oh yeah, the bound of the number of coins is important. So the number is less than or equal to 15, because otherwise you have too many coins, and then that's bad. Yeah. Like you have too many good points, and then that's bad. So yeah, that's like how this question was. Like,
Could you maybe do that, but like 5 times slower?
oh.
Yeah, because not everyone will have one that I can guarantee. Yeah. Can you start from like the classic DP because
Sure.
everyone will have seen that?
Sure. So the classic DP works like the classic DP works like your DP of IJ is like your longest common subsequence.
The entire whiteboard.
Oh, it's like it covers it up, like.
Yeah, like you just gotta run it.
So the idea is your original DP works like DP IJ is like your longest common subsequence for like the first I elements of array 1 and then j elements of array 2. And then like the recurrence would be something like dp of ij is equal to dp of I minus 1 j minus 1 plus 1 if like array 1 of I is equal to array 2 of j. Right? So like if the elements are equal, then I take that element and then I increase the indexes for both like dimensions of the DP because I took that element. And then if that's not the case, then your DP of IJ is just equal to the max of DP like I minus 1 and then j and then DP of I and j minus 1. Right? So this is like your normal longest common subsequence problem. So this has a complexity of the length of array 1 multiplied by the length of array 2, right? Because it will iterate through all of the positions in like this DB, and the recurrence is constant time. So but then that would be like too slow for this problem because like I think the dimensions can go up to like 10 to the 5 or something, or 10 to the 4 actually. So 10 to the 8 will time out. So the way you speed this up is you think about like what's happening with this DP. So like if I drew it up in like a grid, and I had like I going this way and j going this way, then for every element where for every number that's like shared between like the two arrays, like you mark it, right? Then what this first thing does is that if I hit this point, then I move on to here and then plus 1, right? If this isn't the case, then I just take the max of this one or this one, right? And if like this is the case, then what happens is you can think about it as I just have like coins on like a grid, right? And these coin positions correspond to when the value is shared in the first array and the second array. And the problem becomes, I'm trying to collect as many coins as I can, moving from the top left corner to the bottom right corner. And each time if I collect the coin, I move diagonally rightwards. And if I don't collect the coin, I just move, I can move down or to the right.
It's right across to the spot.
Sure. So then like with this path problem, you can just stack a segment tree lengthwise across the grid, and then you sweep downwards. And then the ith position in your segment tree would be the maximum number of coins that you can collect for the number of rows that you sweep to, and the column that's the position in your segment tree. And then after you process each row, you update your segment tree and you move on to the next one. And then after you sweep down, the max in your segment tree would be the answer of the problem. So you speed the n squared to like n log n or something. Okay, so that's the problem. That's like what they have.
Is because if you had like it means that you can only have like
it means like if you had more, then like you'll time out anyway because like you have to like loop through all the positions. Yes.
Oh, this n case then.
Yeah. Yeah, sure. Yeah.
Heavy cases, case meant like because every time I have a case,
You did this one. Yeah, I don't think anyone. I want to talk about your one. I talk about yours. You can talk about it.
actually like
No, that's what you're thinking about.
but it's like that.
otherwise we can talk about G first because I think it's called J, but
Yeah, that's.
Yeah, we can come back to this one. Wait, talk about it. I'm not pushing it. Wait, I didn't even see you. I was going to talk about it. Like, agree.
Yes.
Do you guys know? Like,
Always-
I didn't implement it. So like, we didn't implement it. Mistakes. In my W.
Yeah, complex and segment trees.
All right, so the general approach for this question is to like try some easy approaches and see where we end up at. Is that
I guess the tissue.
Ravine's coming?
That's it. You have to move like. I got you a current over about like. Like, they make one that just.
That's enough. Right, so just by trying different things, we can notice that if we consider values 2, 4, 6 up until 2n, for values of pi in the input, if one of these values don't exist, then the problem is easy. And that is because, let's just say 6 doesn't exist, 6 doesn't appear in pi, then we can just make up pairs 3, 1, 3, 2, 3, 3, up until 3n. And because 6 doesn't exist as pi, it means that any pair of these, because I'm not sure what the p represents, the left value is 6, it means that the paired sum can't exist. Does that make sense? Okay. Okay, skill. So if 6 doesn't exist as a skill sum, then we can just do these pairs, and the sum of the skills will never be 6, and we're happy. And the same thing can be done with the strengths. So if we look through like 2, 4, 6, up until 2n values of strengths, if one of these values for the strengths don't exist, then we're also happy. So let's just say 4 doesn't exist, we can just do 1, 1, 2, 2, 3, 2, up until n2. And because the sum of any two pairs will have 4 as the sum strength, it can't match with any of the large pairs. So that actually covers most cases. What we're now left with is, because there's like n values, n pairs of values, the only case left is if the values of p is a permutation of 2, 4, 6 to 2n, like if it's some ordering of this, and also the strength is some ordering of 2, 4, 6, 8 up until 2n. And it turns out for this case, we can modify the strategy slightly and also solve this. Any questions? So now we're looking at a case where 2, 4, 6, 8 up until 2n appears in P and S exactly once. So we can look at the paired value where the skill is 2 and the strength is, let's just say, 2x, where x is a natural number. what we want to do is we want to kind of have a similar strategy. We try our pairs being 2x, 3x, 4x, and so on, up until n and x. And any sum of these pairs can't be matched with any of the values because the sum will be 2x, and the pair where this is the right side is 2x, have the left side is 2, and all the sums here will have the scale as larger than 2. What we can't have is 1 and x, so we have to find a way to replace this 1 and x. And basically we can just do 1, and instead of x, we do either x plus 1 or x minus 1, depending on whether x is n or 1. And this works because the pair of this added onto itself would be 2 and something that isn't 2x, which doesn't exist. And the sum of this and anything else, we have the strength as an odd value. And because our strength is some ordering of 2 to 2n, odd values don't exist. So this match with everything else is also fine. And that is the solution.
Constraints, I think your team was the only one who was affected, I think.
Wait, what is
Yeah.
the difference?
Basically, statements said that n goes up to 2,000, but there were a couple of cases where n was 10,000.
Oh, what's that?
The solution is linear, so like it doesn't matter. But yeah, oops. Yeah, I think it suffered your team a little bit, but yeah.
Yes. I was so confused about why it's like 10,000 because the solution is linear, but I realized the checkers quadratic. So it makes sense.
Because to verify the solution takes n squared time.
Yeah. What's the next question?
I
think it's it.
like this is the seventh problem, but we skipped the sixth one.
Wait, so we skipped F, right?
You're wondering like areas and
That's your one, right?
Yeah, I guess our team knew how to do it. We just didn't have time.
Yeah. So
Wait, is there?
yeah. So it's just this one. I mean, you can just talk through. Yeah. Is that?
Oh, is it like? Is the solution you kind of like follow the right wall so you can kind of keep on going?
Yeah, but
Like to find every area?
missing, like, it's just like the top, it's like the first 3 points you do.
I think so.
Yeah. Okay. I was kind of confused about the area squared thing because I thought there'll be a trick to it. It's because it's area squared. I thought like there's some like math magic.
Thank you.
Oh no, it doesn't.
Yeah, probably not, right?
Yeah, and also I thought you would just output all of them in like some order, but like because it's like plus is squared, I thought it was math trick. I guess not.
We use final left. Yeah. That's all the. Yeah, but then it was.
So for this question, you're given a bunch of lines as input, and they draw out some things on a grid, and it kind of forms a bunch of polygons, and the question asks you to find the sum of the squares of the areas. So the first thing of this question is that the input is very hard to handle. We don't know what points are connected to what, and that's just very annoying to deal with. So the first step of this problem would just be to process the input. I guess one thing you can do is just copy some line intersection code, figure out all the points where 2 of the lines intersect, and then kind of like connect them up. Just make a graph, of all of these point intersections and have an edge to the other point is connected to. Or you can do something about the constraints are small, so you can do quite a few things. You can do another thing where you just, for a line, you figure out what integer points are on it, and then you see if that's on any other line. You throw them in a set and something. I'm sure there's many ways to do it. But anyway, from this, so the first step would be to process the input into some nice structure with the points, the important points and lines connecting them. The next step is to find out what the polygons are. And the way you want to do this is just by following an edge and just kind of following the inside of a wall. So from this point, you don't really have a choice to go here. But for this point, you find the line that is the closest anti-clockwise to it. It's probably not connected too much, so you can just try all of them. You find the lines that's closest anti-clockwise, you follow that. You find the line that's closest anti-clockwise, you follow that, and you keep on going until you end up where you started, and now you have the polygon. And you would do something to mark these corners as done, and then you'll just pick another point to start this process at of finding the faces, and you keep on going until you mark everything as done, everything inside as done. And to figure out the size of a polygon, there's a very useful theorem that does that. It's very important to know for ICPC. It's called shoelace. Yes, shoelace algorithm. It's just a formula that allows you to basically use the coordinates and basically easily calculate the area. If you don't know what it looks like, just search it up. It's pretty simple.
You be able to
Like the shoelace or
at least like broad strokes of how it works.
how shoelace work? It's like some
You wanna go?
No, you can do it. I'm not doing it. I'm not doing it.
oh, I'm not sure if I remember it though.
You wanna do it? Go do it. Go do it.
I don't remember.
I don't know how to shoot.
You just like take a point, take the other 2 points next to it, and remove them, get a triangle.
It's because you sort of subtract it.
You should say.
Leave an area. Okay, wait. So
It's like
Draw the triangles to every.
I've
Like you just follow the thing and like make the triangles and add them with signs. Is that the thing?
I think it's like trapeze.
Yeah. That's what it
Is the
is.
triangle one? I mean,
Wait. First of all, what's the formula? It's like you have x1, y1. Wait, I can write y.
But look, you cross the cross product.
y1,
every pair.
x2, y2, x3. And I think you do this times this minus this times this.
I mean, I can just take the thing.
Or is that?
Oh, okay, let's go.
Where's the?
I was using that.
For. Wait. I did complete it.
You can just plot the one which have this.
Nice. I think it's like if you do the trapezium areas with like upper half.
Yeah, like and then it's just like it orders around and
Yeah.
then you come around.
When you go left, when you go
It goes
right, left,
negative.
it's negative.
And then like
No.
like so you sort of in clockwise.
And I think
any clockwise start to be like difference in areas of trapeziums.
Yeah.
Oh, that. Is that a high this one? It's I like it that way. It's just proof by a second. All the way down.
I was also considering using break for this question, but I've realized it wouldn't make much difference.
How's your cross every pair? Like it's actually on and you add it up. Like it was. You cross what? The point. You take the points, yeah. I pretend the vectors mode.
Yeah, sure. So we want to find area of polygon. Suppose we're given the vertices in cyclic order, so as we go around the polygon. So yeah, we're going to do the trapezoidal way, but there is also a way with triangles. Yeah, so important note, area of trapezium is half the height times the sum of the parallel sides. Yeah, and so this is literally all it is. And why does this work? Where did I put the thing?
Yeah.
Where did I put the?
Oh, the sound like.
Yeah, this will do. Right.
It was on the floor, but.
Oh, right. Yep.
Every single point class the plus part.
It's literally this, right? This is the thing that you were talking about?
Yeah, I think so. And subtract. Left. Oh, I can bubble. Let's multiply. Like scale level. Can you make this like scale this?
Okay, so we have point x1,
Oh, yeah.
y1, and point x2, y2, and this is one side of the polygon. What I'm going to do is, suppose y equals 0 is down here. It's completely arbitrary what height we call y equals 0. We're going to see later on that this doesn't actually make a difference. But say we're going around the top envelope of the polygon for now, right? So for now, we are going to work out this entire area under this segment. And the area under this segment is a trapezium. It's a trapezium with parallel sides y1 and y2 and length x2 minus x1. So the area going from point 1 to point 2 is x2 minus x1 times y1 plus y2, all divided by 2. So far, so good. Now, if I continue on to the next point, x3, y3, then I can again find the next area, A23, under that line segment, and so on and so forth, right? So we can continue along the upper envelope, so to speak, but at some point we're going to come back, right? Because it's a polygon, we're going to close the loop, and so we might have something like this to x4, comma y4. All right. Now at this point you might say, oh, we're going to we don't want to add this area again, yeah, because like we've already counted this area towards the previous trapezium. That's fine. We're actually going to not add it, but subtract it. And importantly, because we're doing x2 minus x1, then x3 minus x2, x4 minus x3, x4 minus x3 is negative. So where this polygon was added, this next polygon is going to get subtracted, and we're going to exactly discount the area that we overcounted by. Yeah. And here, again, to x5, y5, again, the area under this line segment was overcounted before. It was counted when it was not really part of the polygon. And as we go right to left, we're going to discount it and thus get back to just the actual area within the polygon. Now, I've hopefully convinced you that this works at least for convex polygons, right? You might need to think about it some more when it comes to a non-convex polygon. So what happens if we go to here to x6, y6? Now we are adding again. Yeah. And this may kind of mess with your head a bit because we've gone like the areas here have been added once, subtracted once, and now added again. But we're going to later subtract again as we go right to left. And so again, that's going to get counted 0 times. This area was added once, subtracted once, and added back. So it's going to get included. This area was only added once and subtracted once, so it counts 0 times. This area was added only once and never subtracted. And everything just works. Now, I urge you to think a little bit more about why this works. You know, is a very nice diagram, very nice example where it works, but like, why does this generalize? Worth thinking about. But yeah, this is the idea. You just treat every segment as being a trapezium down to the y-axis, add the signed areas of the trapezia, and it completely adds up to the polygon area. Finally, I said earlier that it doesn't matter where the y-axis is drawn, right? Even if this y-axis had been drawn through the middle of the polygon, doesn't make any difference at all. Why is this? It's because when you shift the entire polygon up and down, all you are doing is adding the same constant to every one of these y values. Yeah. And those y values, like the constant that you add is going to get counted positive for all the forward distance that you go, or the left to rights. It's going to count a negative for all the right to lefts that you do. And because it's a polygon and it's closed, you must do the exact same distance right to left as you do left to right. So it all cancels out. Okay. Neat. Yeah, hope you learned something from that.
Probably one of the most interesting things.
Nice, I'm really glad. And yeah, there is another way where you basically treat one point as the anchor, and then you walk the rest of the polygon, treating it as triangles emanating from here. So you do the triangle of point 1, 2, 3, the triangle of 1, 3, 4, the triangle of 1, 4, 5, etc. And again, you do signed areas of those triangles, and in much the same way, when you go back, when you double back on yourself, everything cancels out. Exactly right. Yeah. Cool. Okay, that is the 7 problems from today. I hope you enjoyed. Today, I just want to acknowledge first, though, that today's problem set was considerably harder than last week. So good job for challenging yourselves. And yeah, like, do not feel disheartened if you solved your problems today. Everyone solved fewer problems today than last week. All right. The next SPAR round is running on the 24th of May. So that is around the end of T1 exams or so. Sorry? Around end of exams. So that's a 5-hour full contest on a Saturday. And then there will be a couple more during T2. So keep an eye out for emails. Follow the SPAR and follow the SPCPA and CPM SOC Discords. And anything else that you want to plug for CPM SOC before we go, Frank or anyone else? Kyle?
Workshop on there's a dynamic programming workshop on Friday. So if you're interested in dynamic programming, please come.
Yeah. So problem D was very much dynamic programming and like a classic DP problem, and then with an extra twist. So yeah, definitely if you want to get better at those kinds of problems, come along to the workshop.
It is this Friday in the evening. Details are probably on the CPM SOC Discord.
SPAR4.
Oh, right. SPAR4 is the 24th of May. It's a Saturday. Yeah.
The 27th of April, but is that the wrong day?
I'm pretty sure that's. Oh, is it? Okay, it's definitely not April. There was like the web page at some point had a mistake. It said April instead of May. That should have been corrected by now. But yeah, it's definitely May. It's a Saturday and the end of May. It can't be both of